A limit is the value that a function approaches as the input values approach a specific point. What does this mean? Let's say we have point A. Let's also say I am moving towards it. What if I move really close to point A, but I never reach it? Well, then I am approaching it. The distance between me and point A gets infinitely small. What about a different example? Instead of approaching point A, now I'm approaching a wall. As I walk towards the wall, I'm hit by a shrink ray. I'm now much shorter, and it looks like I am the same distance from the wall. I'll walk a bit more, and again, I'm hit again by the same shrink ray. Imagine this process repeats infinitely. My height will get smaller while I get closer to the wall. This is a rough analogy as to what a limit represents. As I approach the wall, my height tends to 0, while the distance from me and the wall also tends to 0. Imagine if I represented my height at any given time with a dot, and represented the distance from the wall with dashed lines. As I moved closer to this wall, my height decreases, and this dashed line gets shorter. Our limit, the approached value of our height in this case, is reached when our distance from the wall approaches 0. Now we'll define limits rudimentarily with some graphical examples. Take this graph for example. Instead of having our value approach a wall, let's approach this red dot instead. If we define it as x equals c, then we can see it achieves a similar effect to using a wall. Now let's get 2 other green points along this curve. I will use 2 dashed lines for each dot to represent the distance from the x and y axis. When the dots move around, the dashed lines get longer or shorter. Now, let's have their values approach this x value from both sides. When the green points converge onto the red dot, their dashed lines also converge. It doesn't matter where the red dot starts, whenever the 2 dots converge onto one singular point, in this case the coordinates of the red dot, a limit exists. Stemming from this definition, this is the value that a function approaches as the input values approach a specific point. Now, we say this as the limit as x approaches c for f of x is L, or less mathy, as x approaches c, f of x approaches L. Where f of x is our function, c is the x value that the points approach, and L is the y value that the points approach. Look again, with the dotted lines showing the dots approach L from the left and right. Now, the way we write this is by putting a lim for limit. Under that, we put x right arrow c, or whatever variable approaching any constant. Then, to the right, we put our function, in this case f of x, and then equals L, or the number of your limit. Using an actual graph, we can also define this. Let's say f of x is equal to x cubed. I want to see the limit as x values approach 2. So I look at x equals 2, and I see that when x gets close to 2, the y value gets close to 8. So the limit as x approaches 2 of x cubed is equal to 8. Easy, right? Well, one may see this and think, so why is this useful? Can't I just evaluate the function at that point? Yes, you can in many cases, but the limit is not the function's output. It's the value the function's output approaches. For instance, if I gave you this, would you be able to tell me what 0 is by substituting? No. But if I look at the graph, I can clearly see that this value approaches 1, even though f of 0 does not exist. And don't worry, eventually you'll be able to evaluate this limit without a graph. And by the way, the process of substituting the given x value from the limit into the function is called direct substitution. You should always try this first to see if it really is that easy, but in many cases it's not. It may require simplification, using trigonometric identities, estimating from tables, or calculus techniques to evaluate. Before any of that, let's look at graphs. Here we have some wacky graph with turns and sharp edges and undefined points. Let's analyze if the limits for these points exist. Let's look at the first point. There's a sharp, weird turn, but that's fine since the point approaches from both sides quite clearly. Now, the second point. Here, we don't have a value, but rather a hole. But seeing from both the right and left, I can tell that the values approach the same value, even if the point itself doesn't exist. Thirdly, we have this very odd-looking section. For a limit to exist, both points have to approach the same y value. This helps us stay consistent. Here we see 2 points. Yes, on the left side, the function is defined, but the right side is not defined, and they are not connected. This means the limit does not exist. We see it does not exist because our definition states a limit is the value that a function approaches as the input values from both sides approach a specific point, and these are 2 completely different values. We're going to see another odd graph in a second, but make sure you hone these down. If something doesn't stick, re-watch this video and refer to a textbook if you have one. Now, let's see another graph. Right off the bat, we start off with a vertical asymptote. In this specific example, the graph from the left and right both approach infinity. Even though it seems strange, this means that the limit at this point is infinity. However, this isn't always true for asymptotes. Right next to this, we have another vertical asymptote, except this does not have a limit. Do you see why? Well, it's because from the left of the vertical asymptote, the value tends down, and from the right, the value tends up. Since it's in different directions, the limit does not exist because these are 2 separate points. The last one I will show you is this one. Yes, this graph looks insane. It looks like a jumbled mess, and since the y values oscillate constantly, the value at 0 simply does not exist. But surprisingly, the limit does. We'll see why in another video. Again, if you are confused and want to read the equations again, go back in the video and refer to a textbook or other resource. Now, we are heading to a territory free from graphs. Evaluate the limit as x approaches 3 of 2x squared plus 4x minus 1. Of course, it is quite difficult to graph this function and determine the value faster than using direct substitution. If we substitute 3 in for x, we get that the limit is 29, which conveniently is equal to f of 3. What about this limit? The limit as theta approaches pi of sine squared of theta plus cosine squared of theta. There are 2 ways to go about this. First, you can realize this is a trigonometric identity and simply is equal to 1, or you can evaluate manually. It is crucial you look for trigonometric identities, as they can simplify problems tremendously. For example, the limit as x approaches 0 of sine of 2x over 2 sine x cosine x. Sine of 2x is an identity that is equal to 2 sine x cosine x, and thus this limit can be simplified to the limit as x approaches 0 of 1, which is just 1 as there is no x to substitute in 0 anymore. Let's do one more limit. The limit as x approaches h approaches e of ln of h squared. From your logarithmic identities, you should bring down the 2, and also recognize ln of e equals 1. This makes the limit possible by hand. If you are not comfortable with your precalculus identities for logarithms, sinusoidal functions, sine, cosine, etc., or others, brush up on them as you go through the course. Many functions need these variables and identities to represent real-world situations. Before I end the video, let me state the definition one more time. A limit is the value that a function approaches as the input values approach a specific point. There is another way to define it, known as the epsilon delta definition, that you may see in your textbooks. I know I did, and at first it was baffling and confusing, but as I dedicated myself to my understanding, I eventually comprehended what was in that book.